The Dartmouth Conference established various research tasks for artificial intelligence and gave rise to and nurtured the earliest group of researchers. Following this conference came the first golden age of artificial intelligence, with a multitude of astonishing AI programs emerging and many new research directions continually appearing. Let's take a look at some of the research achievements during this period. Reasoning as search. Reasoning is a high-level intelligence and has always been a core issue in the field of artificial intelligence, as it represents the most powerful form of intelligence in humans, surpassing that of other animals. Interestingly, reasoning seems more intuitive and easier to understand and formalize for humans, and thus, it achieved early success in the field. Early logic included descriptions of the laws of reasoning. Reasoning as search is a method that involves trying all possible choices, eliminating incorrect ones, and ultimately arriving at the correct answer. This is what we commonly refer to as exhaustive search. When tackling complex problems, researchers faced significant challenges due to the vast search space, resembling an endless maze where the number of possible paths grows exponentially with problem difficulty. Therefore, the rapid elimination of incorrect choices to enhance search efficiency became crucial. Alan Newell and Herbert Simon attempted to generalize this algorithm to general cases through their general problem solver program. Herbert Gellerner's geometry, theorem prover, symbolic automatic integrator, SAINT, written by Minsky student James Slagle, also left a profound impression. Natural language has always been a crucial research focus in artificial intelligence. Before the Dartmouth Conference in 1956, there was a long incubation period. After the conference, many researchers immersed themselves in natural language processing research, leading to a period of rapid development in the early 1970s. Early research stemmed from the practical demands of machine translation applications. Researchers in natural language processing followed two major directions, one based on symbolic and rule-based approaches, and the other employing probabilistic and statistical methods, known as the stochastic approach. Symbolic and rule-based natural language processing originated from the early 20th century linguist Ferdinand de Saussure. Considered the father of modern linguistics, his ideas laid the foundation for the development of linguistics and semiotics in the 20th century, making him a founding figure in both disciplines. Stephen Kleene, a pioneer in formal language theory, studied finite automata and regular expressions in the early 1950s. Another notable figure is Noam Chomsky, often recognized as a philosopher and social activist, but also an outstanding linguist regarded by some as the father of modern linguistics. In 1956, Chomsky introduced context-free grammar and applied it to natural language processing. His book Syntactic Structures was published in 1957, proposing transformational generative grammar. Subsequently, Chomsky and other researchers expanded and refined formal language theory. In the late 1960s, they also conducted research on formal logical systems. These studies had a significant impact on natural language processing at that time, and continue to be crucial theoretical foundations for theoretical computer science, formal languages, and programming languages to this day. In 1948, Shannon applied the probability model of discrete Markov processes to describe the automaton of language. Subsequently, he incorporated the concept of entropy from thermodynamics into probability algorithms for language processing. This marked the origin of probabilistic and statistical methods in the field. Overall, during this period, both the symbolic and stochastic approaches achieved significant advancements, but the symbolic approach was more favored. Around the same time, Joseph Weizenbaum created a chatbot named Eliza. Users conversing with Eliza sometimes mistakenly believed they were talking to a human, but in reality, Eliza had no understanding of what it was saying. It simply responded according to predefined patterns or reformulated questions in a grammatically correct manner. In the Golden Age, another noteworthy development was the perceptron proposed by Frank Rosenblatt in 1958. The perceptron simulated the human neural network, and Rosenblatt was very optimistic about its potential. Throughout the 1960s, research in this direction was highly active. Here's an interesting point to add. There were two major approaches to the implementation of artificial intelligence at that time, namely the symbolic and connectionist approaches corresponding to formal systems and neural networks. The relationship between these two approaches is somewhat similar to the particle and wave theories of light and physics. In my personal opinion, the particle theory can correspond to the symbolic approach, and the wave theory corresponds to neural network. Moreover, I believe their ultimate fate might also be similar, mutually dependent, and indispensable. During the first golden age of artificial intelligence, researchers were generally optimistic and liked to make some astonishing predictions. For example, in 1958, Alan Newell and Herbert Simon predicted, within 10 years, digital computers will become international chess champions. Within 10 years, digital computers will discover and prove an important mathematical theorem which has not been achieved to this day. It wasn't until the 1990s when IBM's Deep Blue defeated the international chess champion, Garry Kasparov. Although it was more than 20 years later, it wasn't too far off.
只有学习让我快乐，只有知识让我爆满，只有文化让我充实，只有两学一做才能。
65, Herbert Simon predicted again, within 20 years, machines will be able to do everything that humans can do. In reality, machines are indeed gradually taking over human tasks, but they are far from reaching the extent of taking over everything. In 1967, Marvin Minsky believed that, within a generation, the problem of creating artificial intelligence will be substantially solved. In 1970, he further predicted, within 3 to 8 years, we will have a machine with the average intelligence of a human being. In reality, we have not fundamentally understood the working principles of intelligence, and it is impossible to create artificial intelligence that matches human intelligence before this understanding is achieved. Researchers' underestimation of artificial intelligence faced criticism more than a decade later, in the 1970s, when it encountered bottlenecks. Even the most outstanding AI programs of the time could only clumsily solve a fraction of the simplest problems, lacking any practical value and relegated to being mere toys. This period saw the first downturn in artificial intelligence from 1974 to 1974 to 1980. The difficulties during this period were mainly reflected in several aspects. Number 1. The computing power of computers at that time was far from sufficient. Number 2. The complexity of computations resulted in an exponential explosion of required time. Number 3. There was a lack of recognition that a substantial amount of common sense and knowledge is essential for reasoning. For instance, machine vision and natural language both require extensive knowledge about the world. Number 4. Moravec's paradox. The uniquely human high-level cognitive abilities, such as reasoning, require very little computational power, while unconscious skills and intuition demand substantial computational power. This led to slow progress in research areas such as machine vision and natural language recognition. The concept of this paradox was elucidated in the 1980s by Hans Moravec, Rodney Brooks, Marvin Minsky, and others. The frame problem and the qualification problem are both issues in the field of artificial intelligence. The frame problem refers to the fact that specifying which conditions an operation changes doesn't mean that all other conditions remain unchanged. The core of the qualification problem is that it is impossible to list all the necessary prerequisites for artificial intelligence to achieve the expected results in the real world. In my opinion, both of these problems foreshadow that if we attempt to implement artificial intelligence based on formal methods like rules and logical calculus, the complexity of the real world will lead to an exponentially growing complexity of rules and computational efforts. Research into these problems led to the emergence of new logics, such as non-monotonic logic and modal logic. Due to slow progress, research funding stagnated, many projects, especially basic research without clear direction and tasks, lost funding support. Researchers also faced numerous criticisms. Philosophers opposed some of the researchers' claims, and I believe these criticisms are quite reasonable. Let's take a look together. John Lucas argued that Gödel's incompleteness theorems had already proven that formal systems, such as computer programs, cannot determine the truthfulness of certain statements, but humans can. This is similar to the law of conservation of energy, advising us not to create perpetual motion machines. Yet, we persist against it. Hubert Dreyfus sarcastically criticized some foundational assumptions of artificial intelligence, arguing that human reasoning primarily involves a small amount of symbol processing and is mostly concrete, intuitive, and subconscious know. How? John Rogers Searle proposed the Chinese room experiment in 1980, attempting to demonstrate that a program does not understand the symbols it uses, addressing the so-called intentionality problem. Searle argued that if symbols lack meaning for the machine, it cannot be considered thinking. I believe the criticisms from these three individuals are entirely valid. Even today, these critiques are worth revisiting. The difficulties of computational complexity, Moravec's paradox, the frame and qualification problems, etc., all point to one thing. Symbolic logic is far from the entirety of the human mind. Formalization can only cover a tiny fraction of human cognition, especially considering Gödel's incompleteness theorems that demonstrate the limitations of formal systems. Searle's assertion serves as a compelling response to those who believe that large language models have already achieved self-awareness. However, I do not completely negate the achievements of predecessors. Symbolic logic and formal systems are crucial markers that distinguish humans from animals, but they must be based on other vast unconscious skills and intuitions. During this period, Joseph Weizenbaum began to contemplate ethical issues related to artificial intelligence. In his 1976 book, Computer Power and Human Reason, he expressed concerns that the misuse of artificial intelligence could jeopardize the inherent value of human life. In terms of research directions during this period, connectionism fell out of favor. In 1969, Marvin Minsky and Seymour Papert published perceptrons suggesting severe limitations of perceptrons. Due to Minsky's significant influence in the field of artificial intelligence and Rosenblatt's death shortly after the release of perceptrons, research in connectionism stagnated for a decade. In the realm of formal systems, a notable achievement from the NEETs was the development of the Prolog language and expert systems. Prolog, a logic programming language based on predicate logic, was established by Robert Kowalski at the University of Edinburgh in 1972. Prolog was widely used in North America and Europe, particularly in the development of expert systems. Its success did not deter critics, with a major criticism asserting that humans do not use logical operations when problem solving, a claim supported by psychological experiments. However, researchers at the time, such as McCarthy, overlooked these viewpoints. On the other side were the so-called scruffies, who opposed the minimalists, including Marvin Minsky, Seymour Papert, and Roger Schenck, among others. They recognized the challenge of expressing imprecise concepts through logic. Minsky proposed the concept of frames, and Schenck introduced scripts, a variant of frames. Many years later, object-oriented programming adopted the concept of inheritance from the research on frames. Starting in 1980, artificial intelligence entered a period of prosperity. In the 1980s, expert systems, a type of artificial intelligence program, began to be widely adopted by many companies, making knowledge processing the focus of AI research. In essence, expert systems are computer program systems that simulate human experts in solving domain-specific problems, essentially consisting of a knowledge base and an inference engine. Expert systems are limited to a very narrow knowledge domain, avoiding common sense issues, and their simple design makes them relatively easy to program or modify. The practicality of such programs has been proven. Expert systems led AI researchers to recognize the importance of knowledge, highlighting the close relationship between intelligent behavior and knowledge processing. Their attempt to address this issue involved building a giant database capable of accommodating all the common knowledge an ordinary person knows. However, this ambitious project remains unfinished to this day. During this period, another significant event was the so-called fifth-generation computer project in Japan, which aimed to create machines capable of conversing with humans, translating languages, interpreting images, and reasoning like humans. Controversially, they chose Prolog as the main programming language for this project. As history has shown, Japan made a wrong turn in the technological tree of computer development, while the United States made the right move by creating the Internet, becoming the pioneer and dominant force in the era of the Internet. Another positive development was the renewed attention to connectionism. In 1982, physicist John Hopfield demonstrated a new type of neural network, now known as the Hopfield network, that could learn and process information in a novel way. Around the same time, prior to Paul Werbos, David Rumelhart extended the backpropagation algorithm, a neural network training method. These discoveries rejuvenated connectionism, which had been abandoned since the 1970s. In 1986, the collection of papers Parallel Distributed Processing, edited by Rumelhart and psychologist James McClellan, was published, providing a unified and advancing perspective on connectionism. While people were embracing expert systems, researchers who had experienced the first AI low point anticipated the disappointments people would face. They coined the term AI winter to describe this period. In 1987, the demand for AI hardware suddenly dropped. Expensive AI machines lost their reason for existence due to the continuous improvement in personal PC performance. Moreover, the maintenance costs of many expert systems were high, making them difficult to upgrade, use, and fragile, with practicality limited to a small specific range. People's attention shifted to projects that were easier to succeed. In the late 1980s, some researchers proposed a new AI solution. Their approach was so straightforward that true artificial intelligence must have a body, capable of perceiving and moving, just as humans and animals can survive. They believed that seemingly low-level skills, such as perception and movement, were crucial for higher-level skills such as common sense and reasoning. Abilities like abstraction and reasoning were considered the least important and most boring skills for humans. This viewpoint confirmed Moravec's paradox. Therefore, they advocated for creating intelligence from the bottom up. This assertion revived cybernetics, which had been dormant since the 1960s. This marked the emergence of the third school of thought in AI. The behaviorist school, another figure in this movement, was David Marr, who had deep expertise in theoretical neuroscience. Taking an opposite stance, he rejected all symbolic approaches, believing that achieving artificial intelligence required understanding the physical mechanisms of vision from the bottom up, with symbolic processing coming afterward. Here, let's highlight a small advancement. Geoffrey Hinton, often referred to as the father of deep learning, invented the backpropagation algorithm for multilayer perceptrons in 1986. He applied sigmoid, or nonlinear mapping, laying the groundwork for the next wave of enthusiasm in deep learning and artificial neural networks. In 1990, Rodney Brooks, a robotics researcher, published a paper titled "Elephants Don't Play Chess," criticizing the physical symbol system, our formal systems. He argued that symbols were not essential, and the key was to perceive the world frequently enough. Additionally, during this era, many cognitive scientists opposed intelligent models based on symbolic processing, believing that the body was a necessary condition for reasoning. They elevated this theory to a philosophical level. Let's take a moment to review the 3 to 4 decades since the birth of artificial intelligence. Personally, I believe that the initial flourishing of the symbolic approach had a logical inevitability rather than researchers going in the wrong direction. In the early days of artificial intelligence, also in the early days of computer science, human theoretical knowledge in AI mostly favored the development of the symbolic approach. Logic had a development history of over 2,000 years and evolved into a rigorous mathematical discipline in the mid-19th century. Creating formal systems on this foundation seemed natural. On the other hand, although the working mechanism of neural networks had been discovered, its true workings had not been explicitly elucidated. Even today, we lack a complete theory to explain its entire working mechanism. While other probability and statistical methods effectively handle many intelligent problems, we haven't fully understood their mysteries. We simply use them because they are accurate and practical. This problem persists to this day. Another, more demanding fact is that the computer performance at that time was far below the basic requirements for achieving general artificial intelligence. Even with the adoption of formal systems, we still had to face an exponential explosion of computational complexity. Implementing neural networks based on probability and statistics in artificial intelligence required massive computing resources. Despite facing various failures, this process remains valuable. In this process, mathematicians invented new mathematical tools. Philosophers, cognitive scientists, and psychologists delved into the essence of intelligence, and AI researchers created various tools and theories. Many of these elements became part of the entire field of computer science and were applied to the technology industry. All of this prepares the ground for the next breakthrough.